All right. Thanks very much for joining us. We have a wonderful lineup of speakers today, all focused around the idea of how do we see through cover? What tools do we have that have come up recently? What exciting new applications can we use for this fiendishly difficult task of exploring through covered terrains? So I think we have 8 speakers, and I'm happy just to roll straight into the talks. So the first speaker that I have today is Sebastian Wong from Geoscience Australia. So did you want to unmute, share your presentation and give us a bit of background about what you're up to, Seb?
Sure, no worries. Please let me know when you can see my presentation. Good?
Yep, all good.
G'day. So my name's Sebastian Wong. I'm the 3D activity leader of geoscience integration at Geoscience Australia. So I'm going to talk to you about our continental-scale interpretation of airborne electromagnetics, or AEM. So first of all, I just want to acknowledge that this interpretation was done as part of the Exploring for the Future program, and there's been a lot of people involved in this who are listed here, and also organisations that we've partnered with. So first of all, just some motivation behind our work. So in the team that I'm in, we collect a lot of depth estimates from across the continent, and we want to store them in our estimates of geological and geophysical surfaces database, which I'm going to refer to as EGGS. And that's where the AEM interpretation comes in, because AEM is an excellent tool to capture a large amount of those depth estimates. Just some examples of how we use these depth estimates. So we extract the data from EGGS and we create cover models for them. And then these are in turn used in our mineral potential mapper and our economic fairways, which is a resource extraction economic viability tool. So this is just one example of how we use the data that's in EGGS and our depth estimates. So as you're probably all well aware, Australia is a very large continent, and a large part of that is covered by Cenozoic, Mesozoic, and older cover over more prospective rocks for, say, minerals exploration. So, for example, here in the Mount Isa area, these dark-coloured polygons are the Mount Isa inlier, but we have the lighter-coloured yellowy sort of beige as the Cenozoic, green as the Mesozoic, and blue as the Paleozoic cover in this area. But we now have this the regional geophysical data sets, non-invasive, and it allows us to see through that cover. So what you're seeing here is just an animation of some of our interpretation superimposed on that geophysical data set. And what I just want to show here is how we're really moving away from surface geology and trying to understand what's going on underneath as well. So when working at such a large scale, we found that the best chronostratigraphic scale to map at is the geological error scale. So for example, that's the breakdown of the Archean and the Proterozoic overlain by Paleozoic, Mesozoic, and Cenozoic stratigraphy. And it's the delineation of the geoelectrical features that we can interpret as these chronostratigraphic boundaries, which we set out to interpret. And just for reference, the interpretation is loosely based on the colors of those geological errors as well, the rest of the presentation. Why is this important? Well, those overlying Cenozoic, Mesozoic units, they're prospective for groundwater, but they obscure our access to the underlying rocks, which are more prospective for minerals and energy, and they also hold groundwater resources as well. So to do this, we've had to develop a new workflow that allows us to capture and attribute a large amount of interpretation-specific metadata to each point or interpretation line. So some examples of that metadata are the stratigraphic units above and below the interpretation, the confidence of those units occurring in that area, the confidence of the line placement, hydrostratigraphic information, and so on. And when we're doing these interpretations, we are integrating the AEM with a range of geological and geophysical data sets, which we can help to make the most well-informed interpretation possible. So this workflow has been made as open format as possible. That means that it works on a range of GIS and 3D software packages, including open source software. The outputs are not bound by any proprietary limitations, and then they can be brought straight into our X database, and they're formatted for our 3D layers on our portal as well. If you're interested in this workflow, we have published this recently, and if you go to our electronic catalog, you can find that there. So just before I get into some examples and some case studies, I just want to go over the color ramp that we're going to be looking at. So it's resistive blue, conductive red, and here's just some typical rocks that and sort of what the colors they could be. But this is also dependent on the degree of weathering and the presence of fresh or saline water. So just a real world example here, we've got a conductive horizon overlain by a more resistive horizon overlain by another conductive horizon. And when we start to integrate this with geological or lithological information, we can see that those conductive horizons are more clay rich and the resistive horizon is a sandstone, so more quartz rich. So our interpretations begun in the AusAM1 area in Northern Territory and Queensland. And so this animation is just showing you that the interpretation in this area, stepping from the youngest to oldest. So some structures and faults are first stripped off, and then the Cenozoic and these beige and sort of brown colors are being stripped off to expose the Eromanga and Carpentaria Basin in blue here, and the Georgina and Weiser basins in green, and we're left with some of the oldest rocks in this region. So this interpretation has been completed. It's available for download in a range of different formats that works on a range of different platform software packages, and it can be found on different platforms as well. So in our electronic catalog, and there's some publications on it too. So now we're going to get into some specific examples and do a bit of a scale reduction thing. So we're going to start at really broad scale. We're over in Northern Territory at the moment. This is a very large area. It's about 400 kilometres by 300 kilometres in central Northern Territory. And you can see that there's this widespread Cenozoic cover, which is that light colour with some rare scattered Proterozoic outcrops. Just before I go any further, just for reference, this main figure has been rotated, so it's north to the left of the screen. So we can strip off that cover and have a look at what's going on underneath. And first of all, one of the main things that strikes us here is that there's this structural feature through here, separating more resistive rocks from more conductive rocks. When investigating what that is, I've brought in this locator map the major crustal boundaries, and the Wallora suture actually correlates extremely well with this thing. So the Wallora suture was interpreted by Cauchin-Dublier from seismic and potential fields, but it was never interpreted to come so close to the surface. But we can now see this thing extending all the way up to just under 5 to 10 meters of Cenozoic cover. If we have a look at the 36-kilometer depth slice of the magnetotellurics in the locator map on the side here, we can see that there's this conductive feature running very parallel to this structural feature as well. This is really important because these major crustal boundaries have been interpreted to be fluid flow conduits for metasomatizing and mineralizing fluids to upper crustal levels. And so understanding their near surface distribution is really important for minerals exploration. I've also put the digital elevation model on here, and what that's showing is there's a significant topographic offset across this feature, with the southern block popped up relative to the northern block, which shows that that there's been geological recent movement on this feature, and shows that there's the AEM and our interpretation can be used for neotectonic mapping and also have hazard mapping implications as well. And I've just done some rough interpretation of some stratigraphy in the Lambda Trough in this northern package, just to show how we can map through the cover and get a much better understanding about what's happening in this covered area. So these polygons that I've brought in here, they are a Paleo Valley data set that we at Geoscience Australia published about a decade ago, but they did not have the AusAEM data set at the time of interpretation. They did a great job with the tools and data sets they have, but if you look at these ones here in this pink polygon, we straight away see that there's these conductive basins or paleo valleys sitting on top of the more resistive bedrock. If we do our interpretation of these using that integrated workflow, we straight away see that there's areas where we can quite significantly increase the distribution of these paleo valleys under cover. And we can also look at the connectivity between what was mapped as separate paleo valleys. So understanding their three-dimensional structures and connectivity under cover is very important for groundwater resources, especially in such an arid environment such as central Northern Territory. And this just shows our ability to really think about what's going on under cover. So jumping over the fence, we're in Queensland now. This is the Georgetown area. It's actually quite a large area as well. It's about 300 kilometres by 150. And we can see there's a great correlation between the magnetics and the airborne electromagnetics with this conductive and magnetic feature throughout. There's a similar correlation between the gravity, showing that feature matching what we see in the AEM. So if we look at this area in greater detail, the conductive feature was intersected by a borehole. If we look at the map in greater detail, or the magnetics, we can see that magnetic feature is also correlating very well with the conductive feature through here. So if we bring in the surface geology, we can see that outcropping in this area is a pyritic black carbonaceous shale, and this was also intersected in the borehole at the depth of that conductive feature. So this data integration and scale reduction approach can really help us get a better understanding of what's going on under cover and extrapolate and interpolate our observations to covered regions. So we're now able to map this and correlative units to great distances under cover, up to 50 kilometers to the north and 150 kilometers to the southeast. And in some cases that is under over 200 meters of Mesozoic cover as well. And interestingly, down in the southeast, there's rocks of the same group outcropping, which helps us validate our interpretations under cover. So if units such as this are found to have economic significance, then the AEM can be used to broaden search areas, constrain targets, and reduce exploration risk. Jumping back over the fence again, I'm sorry, we're in Northern Territory again. This is the Dulce Basin or syncline area. We know that there's a synform and a basin through here, but we don't really know the internal structures too well, and the AEM helps with that. So if I've brought in a crude interpretation here, first of all, we can start to see some separated depot centers or potential parasitic folding, some faulting, and these kind of observations are really important because this area is known to have phosphate deposits in pink here and base metal deposits in the light blue color here on the interface between the basin and the basement. And being able to map that in greater detail and get a better understanding about some of those internal structures as well is really important for exploration. Likewise, back on the other side of the fence, we're in Mount Isa area. We can extend those observations to further to the east, because what we saw in the Dulce syncline there is the same basin as the Georgina basin here. And so what we can do is really get a better understanding of the thickness of the Georgina basin overlying those Mount Isa rocks extending undercover. And also that interface can be mapped to get a better understanding of some of those phosphate deposits which occur on the interface between the Georgina and the basement rocks. Now we're really stepping in a scale here, looking at the Cammerwheel area. This is a portion of the Cammerwheel map sheet, 250K map sheet. There's some mines and mineral occurrences on this map, but they're not. It's an old map, so I'm just going to bring in some of the more recent data sets showing the major mines and mineral occurrences. And we can see that these things are potentially structurally controlled because they fall on these faults and some of these folds. If we look at the potential fields, the magnetics shows that they're associated with the edges of these magnetic features, and the gravity also shows that they're potentially associated with these gravity highs through here. And it's these potential fields data sets that are typically used as a first pass for exploration to bring people into a certain region. However, they're limited by a sort of three-dimensional sense in that upper crust and near surface, and that's where the AEM comes in. So straight away we can start to see a few things here. We can see that yes, these things are potentially structurally controlled because these discrete electrical conductors are bound by some of those faults. We can also get a better understanding about how some of these the geometry of these host rocks or the mineralization extends undercover. What's really interesting though is that the AEM was not flown, the Oz AEM was not flown just in the explored regions, but some of the underexplored regions as well. So if we look up strike of these major faults through here, we can see that there's no known mineral occurrences or operating mines. But if we jump across to the next AEM section, we can see that there's, sorry, he's still there. My computer's completely frozen.
Yeah, we can still hear you loud and clear, Seb.
Okay, cool, thank you. So if we jump across here, we can see, oh, sorry, just bear with me 1 second.
Yeah, we just lost your screen shared, so.
Yep, I'll have to bring that back. Just give me 1 second. Apologies for that. My computer just wigged out. Sorry, just 1 second. How's that?
Yeah, we can see that again. We're at discrete electrical conductors slide.
Okay, cool. Sorry, I've lost my pointer. Just 1 second. I'm sorry about this. Okay. So I'm just going to skip through some of these. And so what we can see there is that there's similar conductive features on the next line in an underexplored area. And this is a really good story for the Oz AEM because a mineral explorer has credited the Oz AEM as a tool that's brought them into some of these areas out here. They've reanalyzed some legacy boreholes and they've intersected some copper mineralization, and then they're planning a borehole campaign out here as well. So that's a great win for the AEM. So just some other areas that we've interpreted. So this is the Canning Basin area in Western Australia. We've also partnered with the University of Queensland to help with this interpretation. And that's to do our multi-layered chronostratigraphic mapping, but also to look at salt features What we can see here in the blue lines are the salt isopachs for the Malua salt in this area. That's the thickness of the salt from GSWA. And the interest in the salt is because the caverns made in those underground salt bodies have been, or they're excellent storage sites for large quantity of hydrogen. So what we found there was that there's these horizontal lying beds where the salt exists, but there's these zones of deformation around the edges of the salt. And these zones of deformation have been interpreted as potential movement or dissolution of the salt at lower levels, causing that deformation and disruption in the upper surface. So this shows that the AusAEM can be used for salt exploration as well. So more recently, we've been working in the Eastern Resources Corridor of the Exploring for the Future area. So this is an area of interest because it hosts prospective rocks such as the Curnamona Craton and Delamerian origin. However, it's overlain by the Eromanga, Lake Eyre, and the Murray Basin, for example, which obscure our access to those prospective rocks. Again, we can bring in the AEM, and that allows us to see through that cover. One of the first things we see is some of those basins are more conductive than the basement rocks, which gives us a much better understanding of where those basins lie. And so if we look at the Murray Basin as just a really quick case study, we've been able to map internal stratigraphy within the Murray Basin. What's really important here is that some of those units are, such as the Loxton and Perilia sands, host clay-hosted rare earth deposits. So that's really good that we've been able to map them, and also map hydrostratigraphic units in this area where it's an area of intense agriculture, so understanding the groundwater is very important. So if we strip off the Cenozoic and look at the base of the Cenozoic and the underlying stratigraphy, this gives us a really good understanding of what's going on underneath these basins. We've used this data set as a drill hole targeting tool, where the basement was intersected at very close levels to what the AusAEM was saying and our interpretation was saying. So that's good validation for the interpretation. We've also looked where prospective rocks exist and mapped them under, say, the Murray Basin here, for example, and see how they extend under that cover and the thickness of the cover above those prospective rocks. And in areas where exploration was typically focused in where rocks outcrop. Likewise, in the Curnamona Craton, we've been able to get a better understanding of the thickness of cover over those the world-class lead, zinc, silver deposits in the Curnamona Craton. So ultimately, what we're doing, we're stripping off that younger cover and getting a better understanding of what's happening beneath. Something a little bit different, we've paired up with the Geological Survey of New South Wales for interpretation of that COBAR AEM survey, where we designed a bespoke version of our workflow for them to interpret this region. And it really just shows the adaptability and interoperability of our workflow. And it's also a win-win situation for both of us because they've provided a data set that's fit for the X database as well. So in summary, our interpretation has collected almost 500,000 depth estimate points for the X database, each attributed with that large amount of interpretation-specific metadata, such as the stratigraphic unit information. These interpretations cover an area roughly the size of Greenland or Saudi Arabia. They are available in a range of formats. They work in a range of different software platforms, and you can access them over a bunch of different platforms as well. If you're interested, there's a number of EFTF abstracts, Exploring for the Future abstracts written about them, and the workflow is also published. So, so the take-home message is the interpretation helps for cover thickness mapping and depth of basement in your area of interest. These interpretations have a rich stratigraphic unit information, so they can tell you the presence of prospective stratigraphic units and also paleo valley and groundwater features. Using the same workflow means that they're consistent over large areas, and these interpretations meet a range of data standards, and they're not bound by any proprietary limitations as well, so they can be brought into a wide range of software packages. And finally, these interpretations are meant for use in a wide range of uses as well, so in academia, environmental management, resource exploration, and hazard mapping. So thank you, and I've probably gone over time because of that computer crash, and so I'm sorry about that.
No worries. Thanks very much, Seb. We're only a couple of minutes late, so it didn't impact things too badly.
Okay.
We don't have any questions at the moment, so looks like you're off the hook on that front. Just to remind everyone, we've got the Q&A function at the bottom, and we do have a Q&A session after all the talks. So if you've got a question for Seb, either ask it in the chat or the Q&A function, or hold on to it until later. We might scoot along to our next presentation. So up next, we've got Brandon Ma, and he is with James Cook University. Sorry, Brandon. And could you share your screen and tell us a bit about what you've been up to, please?
I think you're on mute, Brendan, if you're trying
Yeah,
to talk.
sorry. I went into the, yeah, can you see everything now?
We've only got the not presentation. Yep, all good now.
All good? Excellent. And you're on the title slide, correct?
Sure are.
Okay, beautiful. Thank you for that. And also thank you for having me on here. So big thank you to GSQ and UQ for inviting me on for this. Today, basically just going through this whole concept of looking at copper isotopes in groundwater as a means for mineral exploration undercover. And really the thing that I wanted to focus on is where we can all go from here working on this together. So without further ado, then we can hop into that. I tend to be a little unorthodox in always putting acknowledgements first so that I don't run out of time and fail to do so at the end. So for this especially, just thank you to everyone here at JCU and of course in EGRU, through which all of these projects to date have been done. And then Mount Isa Mines and Anglo, and of course GSQ, who have been big supporters of this work for quite a number of years now. And then of course our isotropics group, so that's people in bold there, helping to make all this happen. Tom, of course, who's been involved with this, Peter Ray at MIM, and of course Ryan Mather, the initial observations of which is sort of, or laid the groundwork for a fair bit of this, which we'll cover in a moment. Okay, so basically the way that I figure we can go through all of this is kind of look at the impetus of why it is we want to do this. What's the actual basis for looking at copper isotopes in groundwater and how that can be used to, you know, quote unquote, sense copper-bearing mineralization undercover. Going from there to just summarizing quickly some of our most recent work. So this is an expansion basically of our original EGRU project looking at the Mount Isa copper deposit. And then from there, basically transitioning to the sort of where to from here aspect of things, looking at some observations and methodology and where we're at with that and what the caveats are, and that we all, I think, need to really carry with us as we try to continue to develop and deploy this technique. And then just looking at, you know, what's very next up on the horizon, I suppose. Okay, so the whole idea of all this is, you know, we all know copper exploration is intensely important because demand is far outreaching our ability to actually find this stuff and get it out of the ground. So basically our stores of it. So in a lot of ways, that makes copper the crux resource for this green energy transition. And so, you know, that was part of the draw, at least, you know, whatever it would have been 5 or so years back with EGRU to start looking into this and how we can look at metal isotope systems to help us understand how we might explore for minerals like copper elements or metals like copper, but also other things as well. So exactly how this all works in terms of groundwater hydrogeochemistry is basically that, the dissolution or weathering of sulfide minerals, e.g. by groundwater interaction with or copper-bearing ore in particular here. So we'd be looking at things like chalcopyrite and chalcocite. What that does actually via the process of oxidative weathering, generally speaking, is that releases the heavier isotope of copper into the water. And it also can do that for some other metals as well. And what this does is creates a positive isotope excursion in that groundwater where it has been interacting with and weathering copper-bearing minerals. So that's basically what's going on in this figure over at the right. So this is just looking at the copper isotope excursion relative to the sulfide minerals themselves in water. Right, so if your ore composition is more or less sitting at 0, if you weather some chalcocite or some chalcopyrite, you're going to drive the composition of that water in a positive direction in terms of the relative abundance of 65 copper to 63 copper by around 1 per mil, if not significantly more. So by sampling water bores, especially ones that are relatively deep-seated, we can sense then underground ore deposits that are not easy to detect by other conventional means. Another elegant aspect of this, I think, is that it relies on existing holes in the ground. You can go out into the outback and on station land and sample monitoring bores or livestock bores that used for irrigation, that for homesteads, all of that, and you could simply take those and still, generally speaking, oftentimes get a good grid and sampling density to be able to start to say something, with the idea being that you get as many samples as you can, and where you see especially clusters of these positive copper isotope excursions, that's where you might pause to think that you would have mineralization undercover. All right, so in terms of workflow, generally how that operates is we go out in the field, we sample groundwater. In the ideal scenario, we're getting a pristine water sample. So one of the very first things that I'd implemented, I guess, coming into this game was, instead of bailing, which as we all know can take a whole lot of time, especially depending on the recharge in your bores, if we could target, especially if there are enough of them around in a given region, the bores that are actively pumped already, then we could basically be a lot more efficient in our field deployment. But not only that, we can be more certain that we're getting a pristine sample because there's constantly groundwater flowing through anyway. So then from there, we need to be very cautious, which I'll come back to, in actually collecting that sample to make sure that it does not have any contamination, either from the way that we are collecting it or from the ambient environment around it. Oftentimes, these are in areas with a whole lot of dust and therefore potential for exogenous material to get into our samples. From that point, we'll filter it out in the field. You can do acidification in the field. Turns out it's not generally necessary. We bring that back to the lab. We perform separation chemistry. Often that's ion exchange chromatography, which basically separates out that copper from anything else in that water so that we can make robust isotope measurements. So over at the right, the bit of fun going on there with the reference to Jurassic Park is just showing that, analytically speaking, there's quite a bit to this. But after you can work yourself through that in terms of interpretation, it's a much nicer story in that you're looking for a positive isotope excursion. Again, that's a relative enhancement in the amount of 65 copper relative to 63 copper in your groundwater samples, and especially where you see multiples of that in a given area relative to the baseline surrounding it, then you might think that that's where you've got some copper-bearing mineralization. Now, going back to the whole, I guess, necessity of why we need to do that separation chemistry or that ion exchange chromatography, this is basically a schematic view of how the instrument works that we're actually conducting these analyses with. I always like to put this up because it does function significantly different or differently from a standard ICP-MS, which is what you do for a lot of your, trace element assays and things like that. With the main difference being that, we still ionize our samples and send it through this complex bit of kit. But what this is doing that a standard ICP-MS is not, is it is actually splitting that beam of positively charged particles or atoms according to their mass. and not really anything else if you assume that everything is charged in the exact same way. What that means is that these are beautiful and very complicated instruments. It also means that they absolutely cannot tell two things apart that have the same mass and the same charge. For groundwater, that's very important for us because a lot of groundwater has a whole lot of sodium in it. Sodium will mix with this gas that we use as a carrier phase, basically, and to generate our torch and all that sort of stuff in this instrument. That will combine with that sodium and basically create a molecule that has the same exact or very similar atomic mass to copper-63, meaning if you have sodium left in your groundwater or in your solution, it can give you a spurious result. It turns out, it seems like to varying degrees, you can still make interpretations where there is remnant sodium, but in the ideal scenario, we get rid of all of it. Right, so here, this is basically the whole impetus behind this and how this works. And going back to that original paper that I mentioned very early on from Ryan Mather et al. Back in 2013, and this is looking at the Pebble Creek deposit. And the gist here was that exactly as I was just saying, you get these clusters of positive isotope compositions near your deposit. The good thing about all this is it's low impact, it's low cost, it's low maintenance in terms of actually getting out in the field and doing it. You can perform it relatively quickly. If you know what you're doing and the bores are already running, you can do something like 10 or 15 of them in a day, which is quite good. So it provides not only convenience in that sense and therefore cost efficiency, but it provides easy to interpret signals relative to looking at, trace element packages or suites or pathfinders as conglomerates. The other great benefit of this is we all know that trace elements are not always telling us the correct story. And the great thing then about isotopes is that they can indicate mineralization where there's actually no elemental anomaly. And that's basically what this diagram down at the bottom left is showing us, which is that, within deposit, if you're looking at copper concentrations, you're not necessarily seeing that change there. Whereas with the copper isotope compositions, you do see a more significant change in the isotope composition. That's right on par with those observations we looked at when you're weathering things like chalcopyrite and chalcocite. So this is just a really quick run through. So this is one of the original projects that we had looked at with GSQ. And this is looking at the Eloise, Jericho, and Maronan copper-bearing deposits outside of Cloncurry. Basically, we reconfirmed, that previous observation from Mather et al., where we see a positive copper isotope excursion on or near deposits, as well as identifying some other flips of intrigue, if you want to call them that. So skipping a few steps just because of time, we have now done something like half a dozen of these projects. There is a Mount Isa 1.0 and that started it all for us here at JCU, where basically we see the same thing. So a positive copper isotope excursion on or near your deposit, especially when you consider the prevailing groundwater flow, which kind of creates this directional plume, if you will, of that copper isotope signature. All right, that's basically the end of the whole introductory part. And now on to some exciting new results. So one of our most recent projects on this was basically revisiting the Mount Isa area, but instead of focusing just on the deposit itself and looking at it more like a validation study or a proof of concept study, we wanted to step this out, collect more samples, one, see if we actually see a similar thing years later, but also try to understand if there might be other areas of interest in that same domain, while also implementing a whole lot of stuff that has been added in along the way in terms of sample collection protocols and implementing a novel separation chemistry for copper purification, again, all towards making this scalable and robust. And this was done, of course, through EGRU and with our isotropics lab, with our partners being Mount Isa Mines, Anglo American, and GSQ. So quite nicely, the copper isotope data from this study did reaffirm our previous results and sort of elaborated it on this plume structure and directional flow and indicated potentially some other areas of interest, which is great. And then we also did observe, this is the first time we've really looked in a residential area, that you do get, kind of a municipal effect, if you want to call it that, which is that you'll get very similar results when all the water is the same, which kind of makes sense. But the other great thing about this is that it further validates the methodology and that most of these values are very, very similar, as they should be. And going back to that quickly, just to point out, the blue diamonds are that original data that I just showed, whereas the pumpkin colored circles, that is the new data from this study where we collected around 60 additional samples. The other thing that we've been working on with this is developing these sort of statistical maps or Voronoi diagrams, which basically provide us with these sort of probabilistic zones that are sort of defining where these positive isotope excursions are. And then noting as well that going back to that concept of concentrations and isotopes not necessarily giving you the same story, that is the case here as well, which we've been able to show. So this composite panel basically is looking at your copper isotope compositions along with the concentrations of copper and a few other trace elements. So the copper concentrations and isotope compositions don't necessarily match very well. But interestingly, when you look at some other potentially influential elements like manganese and cadmium, you do actually see some overlay or overlap in those patterns relative to the copper isotope compositions. So all in all, this is a successful study. We are really happy with it, and also really happy to be able to provide, I suppose, a complete package and really develop out the protocols to move this forward into the future. So with all that, all very positive stuff, all very exciting, but I do think it is worth spending a bit of time just talking about, where we need to be mindful of what it is that we are in fact doing. So just going back here to, our workflow model basically for how this all happens, and pointing out that we do need to proceed very carefully and make sure that we're ticking all the boxes to have the strictest protocol necessary. So that basically all starts with just the sampling itself. So depending on what guidelines and where you're doing this, conventional approaches can have somewhere around 100 or more ppt copper in your field blanks. So in a 50 milliliter sample, that's roughly 5 nanograms or more, which can be a very significant portion relative to what you're actually trying to measure, especially if your copper concentrations in the actual groundwater itself are at a sub-ppb level, which they often can be. So this can really obscure what's going on with elemental data and especially the isotopic data. To date, we've been able to really improve on that and get our field blanks very, very low. So down below basically the limit of detection on our instrumentation. So well below, in many cases, 10 ppt. Very, very small amounts of copper left over in that, robust trace element data, and negligible influence on our copper isotope data. With the chemistry itself, the conventional techniques, there has been a lot of work there, and that is, I think, working very well. What we've done with that is try to basically streamline it, especially for this sodium removal. So turning that into just a single pass through that separation chemistry, focusing on highly efficient sodium removal, using very weak and low volume acids to limit our blanks, and then seeing if we can do this on more than a 50 ml sample, knowing that a lot of times there's very little copper in this water and we need to actually process more than that to get robust results. And this is really turned around with high reproducibility and good blanks, which I'll go through in just a moment. Also, in terms of the analyses, other things we need to work on and consider is that certain components of the introduction system can enhance these matrix effects by things like sodium. And external calibrants then or other ways of correcting the data do not work or cannot be applied. So if we circumvent that, which we have, then you can apply that doping even though it's not strictly necessary all the time, and get the most robust data possible. So summing all that up in terms of where this is going and how we can make this a tool for everyone and work together towards that is we've now come up with a means to really deploy this in a large scale way and getting reliable copper extraction from sub ppb level samples with excellent sodium removal to get rid of that interference or that spurious result that I was talking about before. We've managed to get our field blanks extremely low and also have no sample prep prior to column chemistry. So you can take it literally from the field and go run it straight through that separation chemistry without having to digest it, dry it down, or do any of that. Low chemistry blanks, meaning what we're measuring is the actual copper composition or isotope composition of the groundwater itself. And just these reproducibility metrics down at the bottom are considered very, very good by any standard, and especially the last one, because if we're looking for excursions on the order of 1 to 2 per mil, if your full procedural reproducibility, basically from the field to a number on a page, is less than 0.5 per mil, then you can reasonably rely on those results. Righto, so what does the future hold? Always room for improvement. So improving chemistry, time efficiency of that chemistry, making sure we're all applying ideally the same exact protocol so we can compare data, improving our yields to make sure we can get as many measurements as possible, and then always being mindful of that bugaboo in there, which is that sodium that can be left over. And then I'll just end here, which is, also on the research horizon. I think it's a good thing to note, and I think it's really positive. This methodology and work like this will still be continuing on here at JCU. However, I myself will be moving on to the University of Melbourne and also onboarding this there, meaning there will be more capacity here in Australia for this type of work. And in both places, already having the instrumentation in Melbourne and then hopefully soon here, new types of instrumentation that can actually remove that interference for us. And thank you. That's all I've got.
Thanks very much, Brandon. We did have a question pop up. I am conscious that we're running over time though. So do you reckon you could have a look in the Q&A section and answer the question from Mike Whitbread, if that's all right, Brandon?
Yeah, certainly. Thank you, Janelle.
Yeah, and then we'll hop on to our next speaker, which is Joe Tang from inside the GSQ. So I'm really looking forward to seeing what Joe has to talk to us about.
Good afternoon. How's the presentation? Can you see
Looks
that?
good, Joe. Thank you.
Okay. In today's talk, I'm going to talk about transforming geoscience concept and data from research, sort of data into an exploration tool. When I talk about undercover here, we are talking about basically greenfield concealed deposits as well as a truly sort of undercover sort of deposits itself. Before I begin this talk, I'll sort of I've inserted a slide from a previous talk. In this slide, it shows two sort of data sets. The blue one represents the sort of mineral discovery over the last decade, and the maroon one shows the amount of EPM applied or granted over the corresponding time. Basically, if you look at the blue trends, there is a progressive decline in discovery over time, and this extends into the last decade or so, despite ever increasing amount of energy and times and money put into exploration. There are two reasons for this. The first reason is possibly that most of the discoverable deposits, that's shallow exposed sort of deposit has been found, and therefore the remaining sort of discovery will be undercover and it's more challenging to find. The second reason that that I could think of by looking through the 3 decades of exploration report is a lot of explorers are still using conventional exploration techniques in unfamiliar ground. In doing so, it reduces the chance of a new find itself. Therefore, to move forward, what we need is new directions, new ideas in exploration, and this is where we come in by introducing new tools in exploration itself. And these tools were generated by work with other collaborators. In this talk, I'm going to firstly examine the different stakeholders in geoscience itself and stress the importance of collaboration as well as knowledge sharing. We are now entering a new paradigm in exploration, especially targeting this decarbonized future. Therefore, to achieve that, we really have to adopt new concepts in the greenfield, undercover, as well as concealed deposit exploration. To do that, I think explorer needs to sort of create new workflow that use existing as well as new data and adopting new ideas how to achieve this. in this talk, I'm going to talk about, collaborative projects that transform baseline and basic data into undercover exploration tool itself. To begin with, we'll look at as what I've done here is to summarize the stakeholders in geoscience into three sort of, spheres itself. The first is the geological surveys, the second are the researchers, and the third are the industry. I'm one fortunate person to have worked in all these different spheres. Basically, the state and federal geological survey and contractors to them has a responsibility to compile regional geology, geochemistry, geophysics, and put this, or synthesize this into models that the other sort of, spheres within the geoscience could use. The second group of stakeholders is the researchers, and this includes universities, Geoscience Australia, CSIRO, and all those linkages, as well as the research centers, ARC, CRC, and etc. They are responsible for innovations, for new ideas, and provide new directions in geoscience exploration. The third and one of the most important things are the industry, the explorers and the miners, because they are the ones that actually translate ideas that's created by the survey and the researcher into practical purposes and, responsible for the discovery. Basically, they are the economic drivers because their tax money and their royalties pays for, our wages in our, project itself. Well, that brings to the importance of collaboration. What collaboration means is that it's between two or more parties, and it's only the signatories of those collaborators could see the result itself. It's a good approach. However, it does not share the data with all the industry. What we really need to do, in the next years or few decades ahead is to actually share knowledge. That's to create knowledge that's open to everybody, and everybody within the sector can see and use those data. And that's the thing that I would emphasize in a lot of this project. That's a shared knowledge. What I'm going to talk about today is to highlight three examples. I know it's really ambitious, to go through three of them, but to look at the three examples of actually transforming baseline and research data into actual exploration tool itself. The first is the National Geochemical Survey of Australia data. In brackets are all the collaborators. The second is the groundwater hydrogeochemistry, and again, those are the partners in this project. And the third is a geochemical toolkit and domain map. As all this product has been completed and all the product, reports, everything released, what I'm trying to do is to basically highlight that these are the tools that the Geological Survey, in conjunction with all our sort of partners, have produced to try and sort of promote exploration undercover or in greenfield areas. And I have included a slide in the last page of this presentation where we have links, and you could download all these reports and all these products through that link. We'll start with the National Geochemical Survey of Australia. Basically, it's a collaboration between Geoscience Australia and GSQ, and we have been very successful in this and extended the same program to the Cape York area, where we engage or get involved with UQ very closely to sort of come up with the output. What is meant by output? These are the reports or product that came out from this project, and I sort of listed this all within the last or the bibliography which you could download this report itself. The ultimate goal or output of this indirectly is this bag of dirt, and I'll stress the importance of the bag of dirt. Well, what's the background of this research? It is a research undertaken by GA and CRC, basically looking at overbank deposits. Instead of taking multiple soil samples, they found that the overbank outlet sediments at the lowest point in the catchment gives the best approximation of a homogeneous chemistry. Therefore, you take only one chemistry that will best represent the chemistry of the catchment itself. And the catchment modeling is based on ANU work through the digital elevation modeling. And the model we use is the NC model. Basically, the bag of dirt that you see, it's what we are aiming for, but the bag of dirt tells you nothing. So we translate that into 68-element baseline geochemistry. Although this is an excellent chemistry as shown in this figure here, it has limited application to explorers. It's a multi sort of use data set. The same data for copper is translated, here into, or crop out for Queensland itself. It's a really hard to use data sets, although I see it as a fantastic data set. So what a Geological Survey of Queensland has done is to put another layer to reinterpret this data, to give or re-rank them according to anomalous sort of value, as well as to give a special sort of attribute to it by plotting this chemistry within the catchment area. What it does is this: it gives explorer the elements to look for, and we have 68 elements, 66 elements in this data set, and as well as a special or sort of locality to look for. Because of the success of this, there's a lot of demand for more work, and the Geological Survey of Queensland has extended this work to the Cape York area towards the north. What we've done is this: we've reduced the catchment size to sub-catchment size at prospect scale. It better defines all the anomalies where companies basically could walk in, look at what elements they're interested in, which catchment they're interested in, and then could start exploration within the catchment without having to do this ground work. So this is an excellent tool that encourages greenfields, as well as these sort of commodities that has not been looked at, in terms of exploration itself. Another use of this data, being a comprehensive statewide, you could actually talk about it as a nationwide database, is that it covers every natural occurring elements. And therefore, you could sort of use this data as a very important first stage in a sort of exploration, in a sort of targeting method. What I've done here is to normalize the Cape York data against the Mount Isa data. And this is really useful because it gives you a visual as well as an immediate sort of targeting tool, where to look for in an area of interest. In this case, what it shows here, these are elements as elevated in Cape York, and these are elements as elevated in Mount Isa itself. Basically, the Cape York area is high in tin, tungsten, and gold, whereas Mount Isa is gold, copper, silver, and zinc. Interestingly, all the modeling shows that the Cape York area is high in lead, and we haven't found a big lead deposits in Mount Isa yet. And therefore, this data set, provides a good first-hand, expression targeting, tool that explorer could use to go into a new area and to sort of define what elements to look for. Another sort of useful, uses of this data is to be able to model this data. Basically, there's many ways of modeling them by using single elements, multi-elements, etc. Here, what we have shown is an example of a modeling where we look at this rare earth, and the green just highlights area of high rare earth, potential areas itself. There are different grids, different ways that you could use this. And in one of the Cape York reports, we have highlighted, the potential, the mineral potential based on different mineralization model itself. And lastly, this is another example. It's not the last, use of that. It's a 2D target size modeling exercise. On the left, you see here is the lithium map, for Cape York area. And on the right, it's the one and only non-hard rock, lithium occurrences that's in the Buchanan Creek, which occurs southwest of Georgetown itself. The background of this is really small. It's really low. So what I've done is this: I model is back to an area, basically to a sort of theoretical area where the source of lithium could come from, and basically models down to, say, for economic grade of 1% or more, it models down to about 0.3 square kilometer area. In other words, it's a very small deposit if you were to sort of find it. And so this is one way you could use this database, because it covers all the natural elements, it covers every part of Queensland. You could use this data, and there's a lot of combination that you could use the data for greenfield as well as mineral targeting exercise. So the next thing I'm going to talk about is the borehole hydrogeochemistry. I'm really glad that Brandon has spoken about the copper isotope, and Robert is going to talk about the next one on hydrochemistry for exploration. And therefore, I'll be really brief on this. This is a collaboration basically between CSIRO and GSQ, and we have get the involvement of all the various uni in Queensland to look at the metal isotopes itself. Again, one of the main sort of target is the thousands of hydrogeochemical sample itself that translate to thousands of geochemical data. I wouldn't go into the background of this project. I think Robert is going to talk about it. But basically, the data set is really good. And I have two terms, that I've used to summarize the chemistry. Basically, the chemistry, it's a proxy to drilling, because instead of drilling, you can look at the chemistry and find out what's underground. And another sort of phrase I've used is that they are props to the subterraneans, because it's that good. Okay. It's a 66 element baseline chemistry, and there are multi uses with that, from environmental to mineral targeting. And what GSQ has done is to combine the chemistry with metal isotopes and use it to target as well as telescope into mineralized zone itself. Because of the success of the work in the Eastern Mount Isa, there's a lot of sort of requests for more work. And so what we've done is that we've extended this work to the Georgetown area, and hopefully we can sum up this in terms of report, towards the later part of next year. I won't go into this, but we'll just highlight that the output is either single elements or combined single elements into mineral system itself. And I'm sure Robert would be talking about this, or you could use this for lithologic mapping. Perhaps in line with this theme of today's talk, it's about resource targeting. The output of this, from the work that CSIRO and GSQ has done is that we have defined 13 areas of mineral sort of potential areas through mineral indices. The other thing that we have used on top of this, chemistry is lead isotopes, where we work with QUT, with Professor Bowles Kemper, to look at the IOCG signatures of lead, for the Mount Isa area. And using that lead isotope, we identified few areas that's undercover that has this IOCG or Proterozoic style signature. One of the most interesting one is in the Clona area, which is basically northeast of Ernest Henry. It has 4 borehole anomalies and real strong Proterozoic IOCG signature. In terms of geochemical sort of exploration, this is an excellent area to find the next sort of big deposits. Other area pick up are the L. Lewis, the Kennington, and a deposit south of Kennington, or area south of Kennington in the Tullabug area. Therefore, this, in conjunction with chemistry, better define anomalous area, and in this case, an IOCG or Proterozoic sort of style mineralization undercover. I won't talk about copper isotope as Brendan has gone into it, and it is another tool that we could use to target mineralization undercover. And the last example I'm going to talk about is the geochemical toolkit and the domain map. This is a multi sort of group, collaborations, and which looks at soil, plants, and soil gas itself. Well, there are 2 parts to this program. The first part, it's a purposeful, sort of study that looks at the geochemical, sort of migration through cover. It's a work undertaken by Adelaide Uni and Keith Hannon. And this work has been summed up in the geochemical toolkit. The second part of this study is to integrate findings from the early study into the domain map. What the domain map is, it's actually an integration of drill hole, geological, and geophysical interpretations. We heard about, talked by Sebastian about, the eggs. And eggs, sort of model has been integrated into this, as well as work by UQ, where they use the depth to basement modeling into that. What we've done is we use this depth to basement and integrate it into the geochemical toolkit to come up with a product that would actually tell you where to look for and how to look for, undercover. This is the content of the geochemical toolkits, where it looks at the different depths to basement, and this is the content, in the report itself. What we've done is this: we've extended that by modeling the depth around miners out, by making it into a domain map itself. And with this domain map, into domain 1, 2, 3, 4, we listed the different expression methodology that you could apply in those various domains. And therefore, it's a real exploration tool for undercover, where you could have an area to look for and one method that you could use to look for. To conclude, basically, what I've done here is to highlight all the various products. These are just 3 examples of products that the GSQ has worked with the other stakeholders within geoscience, sort of fraternity, to come up with new thinking, new tools for green fuels and undercover exploration. As I mentioned in the earlier talk, that there are various stakeholders, and we realize that the various stakeholders has various and very different expertise, and there's really little crossover between those expertise. And therefore, it really highlights the importance of us working together collaboratively and to share knowledge. Because if we start developing within individual sphere, we will never achieve the totality of geoscience experience itself. And so by collaboration and share knowledge, that's how we could. And I think it's this next step into finding more deposits in the future. Well, I do also think the geological surveys have a pivotal role to work with researchers in industry to trial new ideas, as well as to get feedback to and from the industry itself. It's only through this collaborative work we could achieve, the next discovery. Finally, I've summed up all these sort of, publications and work that we have, and the links will lead you directly to the product that you could download for free and use it as a tool in exploration. Thank you.
Thank you so much, Chair. I love that take on how important collaboration is for producing these big scale tools that are so important for exploration. You have sparked a couple of questions in the Q&A function, but I think in the interest of time, I might have to ask you to answer those in text or hold on to them until the Q&A session afterwards.
Thank you.
Thank you very much. Our next speaker is Rob Thorne from the CSIRO. Are you with us, Rob? And
I am
could
indeed.
you share your screen?
Certainly.
Oh, okay.
You're right, Joe. Your screen stopped sharing.
Okay, thanks.
Okay, how's that looking? Let's see. See the presentation?
Not yet.
No, I'll have another go.
I can see it now. Thank you.
Excellent. Okay, well, thank you very much. And thank you, Joseph, for some of the introduction there around some of the work I'll be talking about and highlighting some of the work we've done with GSQ. But I'll also be showing some of the other things around on a more national scale and some other case studies looking at hydrogeochemistry and specifically around that mineral exploration. Firstly, though, I'd just like to begin by acknowledging the Whadjuk people of the Noongar Nation, the traditional owners of the land on that I'm meeting you from today, and pay my respects to their elders past and present. So, hydrogeochemistry and mineral exploration. Really with this talk, I want to run through a little bit around how it can be used in drill fields exploration. We've heard how the sampling has been undertaken on bores and station bores, so you've got about a 2 to 3 kilometer sample spacing sometimes. So that sort of broad spacing means that it's quite apt for this greenfield exploration, and moving down perhaps into tenement selection where you have more samples in a smaller area. Look at how it can and should be used in undercover terrains and why it's useful in those terrains, and then going on to actually looking at what mineral systems can we detect. We know from previous studies that it does do quite well with detecting some mineral systems. When or where might it not work as a technique? So really then looking at those methods and tools we've had a little bit about, I'll skip through some of those perhaps a little quicker, look at the results interpretation and go on to that targeting side of things at the end. So then similar pictures as we've seen before, out in the field, taking these samples from the station bores they use to irrigate and water the cattle and livestock out there. Take a number of different bottles, do a number of different measurements in the field, pH, EH, TDS, those sort of things that might change and ideally need to take at the time. Then send those off for all the major element analysis and minors, alkalinity, phosphate, total nitrogen, and then precious metals that we pre-concentrate on a carbon sachet because their concentrations are so low for direct measurements, especially in saline samples. We'll then also do different types of isotopes. We normally do oxygen and hydrogen isotopes by rote, and then we do other sort of isotopes, and I'll mention a few as we go through with the rest of the talk. So we heard about contamination and the problems around with it, and thankfully there are, when we're looking at just purely at the elements and not the isotopes in this case, we try and mitigate to some extent by putting together a contamination factor. Ideally, we will be looking at those flowing bores, and where we're out in the field quite often now, those field trips are based around looking for those flowing bores, just as we've heard, ease of sampling, and because we're much more confident they're not contaminated. However, we can't always do that. So this contamination factors allows us to gain an idea of the confidence we have in certain elements in terms of their likelihood to be contaminated within that sample, and then we just remove those data from the data set. We can't rely on those for any of the modeling or the looking for these mineralization zones. Then go ahead and perhaps do some multi-element indices, different ones used in different regions depending on the background that we're in. But essentially all of these are designed to help establish different ways of looking at the data, rather than just looking at pure metals, for example. We add those metals together and they're related to different ways that sulfides generally are weathered and produced acid and so on through those systems. And I'll mention a few of those as we move forwards. We also use element ratio. So, for example, a deficit or excess of an iron ratio compared to seawater, just the baseline, to have an understanding how different lithologies perhaps are weathering, and indeed different types of mineralization. And I'll present some few of those, but just to give you a background of the sort of things we're looking at before we get into the data itself. Finally then, and quite new, is the formation of this X3 hydro tool within CSIRO, led by Nathan, Alex Hunt and John, and I was involved in the production of this. But essentially it's a tool that allows you to bring in a lot of that data, do some of that stuff around indices generation, and produce a coherent and consistent, importantly consistent output that is readily interpretable. And that means that we can go back through all the data that we have found available, a lot from water corporations and the like, and produce, and indeed actually this was started back with David Gray, now been going forwards with Nathan Reed, produce a coherent and consistent database in one database across the entirety of Australia. So this is about 320,000 data points now. And with this sort of thing, it's really good for finding the background for where you're going to put your new studies in. So for example, you can quite nicely see the Menzies line running through here with the acidic waters in the south, non-neutral in the north, things like the more alkaline water of the GAB running through these zones here. So actually really, I think, quite important database, and especially looking at hydrogeochemistry. And it really does allow you to provide context to any further studies that you might be doing with any of these regions that you have this background data. Now, of course, you don't always have every element you like for each of these sample points. Sometimes they're just the majors, but you can still get out quite a lot of information from these data. I just want to touch on this sample depth as a specific in terms of a case study and what actually we're doing in terms of seeing through cover in hydrogeochemistry. Of course, with the hydrogeochemistry, you have generally a greater reservoir, if you like, of elements that the water is in contact with. So that larger water rock interaction volume probably greater than generally in the source. So you generally have a broader, perhaps, signature from mineralization. And of course, you're also sampling at depth. So your water table might be between 5, 20, 30 meters. So you're already somewhat within cover when you're taking these samples. So what I want to do is just show a case study here from in the very much in the north of the Yilgarn bottom of the Capricorn region in Western Australia. And we're down here in what's known as the Briar Basin. And this is the hydrogeochemistry data through here. This takes chromium, and this chromium line up very nicely, or the elevated chromium is lining up very nicely with what's called the Narracuta mafic formation in here. So essentially, lithology, very easy to see in this case in the hydrogeochemistry. We just put on top the GSWA source sampling survey. We have some indication of that elevated values here related to mafic rocks, but what we don't see is that really nice extension over to the west that we do in the hydrogeochemistry here. And that's mostly due to the fact that we're having increasing depth of cover due to paleochannels in the region. And we can see that signature of the underlying lithology in the hydrogeochemistry, whereas we can't in any way so clearly and is nicely delineated in the soils. So quite a nice example of seeing through cover, and really the basis for a lot of this seeing through cover as well. Also just mention the relevance of scale. So on the scale of the entire continent, we have here sulfate to chloride ratio, chlorine ratio, and we see that there's some really nice variations in major aquifers and lithologies, essentially is what we're seeing. As we zoom in further to specific deposits, we've got the VHMS deposit here, the Jaguar and Teutonic Bore and Bentley. And we can see here actually that there is very much a variation in this ratio. Now this is interesting. This is either a high or a low number is what we're interested in, because at depth your sulfate is acting as an oxidizer, oxidizing things like pentlandite to avarite, pentlandite to avarite. And as it moves up in the system, becomes more oxidizing, we actually get nitrate becomes the oxidizing agent, and you get the formation of sulfate. So our high or low is interesting. And again, we see here, beginning of that, some of that information that we gained from the studies with GSQ, that ratio delineating some of the regions around some of the deposits in the Mount Isa inline. Let's look a bit more at that data, some of which we saw from Joseph originally, and just to really highlight how we might go through one of these studies in collaboration with surveys or industry. And what we have here is just the major geochemical parameters, or some of them. What we start off, we're looking for patterns with these, any really particularly acidic samples that might be related to sulfide weathering, or is it more of a general trend, as in this case? But you really start to see those general trends quite evident quite quickly. So here, probably different aquifers may be related to depth of cover, and I'll show some more examples as we go forwards, and then just some background context around the salinities. So this lithology mapping undercover, and again, Joseph showed a couple of these, but just to really highlight, there's some very major variations between what are different aquifers most likely related to cover. So here you'd expect to be thinner cover, and you see a signature from probably the underlying crystalline basement still within these waters. In this area, you expect the cover to get quite a lot deeper quite quickly. And again, you can do some of the lithology mapping, look at, I think these are the Brumera metamorphics here with vanadium associated with more mafic lithologies. So begin the study to get the background, get the context, get some indication of lithology and so on about the major aquifer systems within those areas. How might we actually go looking for these mineral deposits themselves? What does mineralization look like? So we can look at different signatures for different types of deposits. So for example, base metals, you're looking at essentially a low EH or O2 saturation as you get the weathering of these sulfides. So iron might be released into the system from things like pyrites, a lower pH formed from the acid that's produced. That acid then might release other elements you might not normally see, bearing lithium, manganese, and so on. And also you might more rarely detectable alumine and rare earths within that system. Now, interestingly, and as we heard, quite often in terms of the copper isotopes and copper, quite often the direct metals themselves don't actually show you where these deposits are, which is why things like copper isotopes are actually a quite nice way of looking at the data. So for example, here again, that's that VHMS deposit, and we saw actually you could see it in the sulfate ratios, but you can't see it in the direct metals, not really, unless you're right in the middle of the mineralization. So here, obviously, the highest concentration here is in the center of mineralization. It's not shown in these figures, but that's where it is. And the copper and zinc, because it essentially isn't transported very far, it very quickly drops out of solution in neutral waters and also absorbs onto those clays and iron oxides in some systems. So you have to be aware of that, and you have to use other indicators and ratios and so on to be able to help designate where mineralization might be. So as I say, use indices and ratios as well. For example, the acid S ratio, which is a measure of elements that might be weathered by acid produced from mineralization, potentially. I would say that we never really use one of these by themselves. We try and layer these data together to get a greater picture and understanding of what is actually present within these waters and what it might mean in terms of signatures. But actually, in this case, lead has one of those elements that might not be transported that far, but there's quite a high background in this region and actually be much more comfortable with using lead in these systems. And that's not to say if you see a copper and zinc, you shouldn't be looking at them. It's just that the anomalies are probably more constrained in a lot of these areas in neutral waters. Gold then, just another example of looking at different systems. Gold is in groundwater is the best target element for gold deposits. So it's quite convenient. We saw Joe's picture come up here, and we can see that many of the gold values coincide with known mineralization, and where they don't, that becomes more interesting. So you combine that with other elements such as moly or anything that might be associated with gold mineralization, and you become a bit more interested in those areas. And sometimes even with a really high gold number, maybe a few precious metal numbers, that's the individual sample, it becomes more interesting. I did want to touch on some different isotope systems and some of the work we're doing there. So as an example, we're back up in the Capricorn region here in Western Australia and around the Paulson's deposit. And in that region, we have really quite high gold values in the water right next to the deposit. Similarly, that platinum, cobalt, palladium, all very high, all indicative of this mineralization. So what we did at the part of this study was actually take the sulfur isotope analysis for the region, I think 300 plus samples, and those samples that were associated with Paulson's deposit. Not only took the sulfur isotopes, but we took the oxygen isotopes from the sulfate. So here you can see in red, essentially, is the data from that deposit, the Paulson's deposit, and that really creates quite a nice population different from the background. And you've got the signatures of the diagenetic and nodular pyrites down here on the left, and the axis there. There's an idea of where these water might be inheriting these signatures from. Now, interestingly, with the oxygen and sulfate, essentially that's inherited from the time that sulfate's been formed from the waters that it's been in contact with or it's formed from. So it's just showing there's a different fluid that has been in contact with these potentially sulfides at the time of weathering. And this is the sort of thing perhaps we might like to progress a bit further. Certainly the sulfide story has been shown in a number of deposits. It'd be nice to have a look at how we can bring other isotopes into these studies as well. And obviously we've seen that with the copper to great success. So really then with this talk, I just wanted to give you a brief sort of overview of the sort of things we've been looking at, the data sets that we have available and the projects that we've been doing, some of the more interesting things around the isotopes. And then at the end of all of that, again, the same sort of figure that Joseph showed around the areas of interest that we produce. So that goes into multiple different types of element ratio, saturation indices, all of which help to build this picture of areas of interest that were going to be more interesting for exploration in the future. And that's it. Thank you.
Wonderful. Thank you so much, Rob. And you've got us a little bit of time back as well, so I greatly appreciate that. We would have had time for questions, but unfortunately we don't have any in the Q&A for you at this point. Right. So it looks like you're off the hook. All right. So our next presenter is Brian Noble, also from the CSIRO. And he's going to talk about a different flavor of chemistry. So,
just a second. There we go. Hopefully you are seeing the main slide.
That's good. Yep.
Excellent. Thank you all. What I really wanted to talk about today, some of you will have seen a little bit of this in the background in the past, but it's really about how we improve our approaches to interpreting soil geochemistry as one of the fundamental sample media we use traditionally. Probably not in the thickest of cover, as you'll see in one of the examples, but there's a lot of areas with shallow transported cover where I think soil geochemistry has a lot of big advantages. And when I look back at some of the past work I did, I went back to my first week at CSIRO nearly 17 years ago, and I presented there we go. Presented what I wanted to achieve while I was at CSIRO, and that was this book. And the reason I wanted that was for me to interpret geochemistry better. And so I've managed to package my work program with a bunch of very talented individuals that have done a lot of really cool stuff in terms of bringing in landscape interpretation to understand our exploration soil geochemistry better. And so hopefully I'll take you through that journey quite quickly because it is a short presentation. But I wanted to go back initially to where it started, which was refining the soil geochemistry projects of soil geochemistry methods itself. So what I will talk about is ultrafine soils, and basically that's the clay size fractions that we've worked on, and then how it's interpreted better. And the reason we came back to this was because we did some test work in the back of the building where, for example, we buried ore. Just trying to get my laser pointer going here, where we buried actual ore materials in the bottom of 2-meter pits in sand dunes and backfilled them, and then carefully started monitoring them over many years. And I was a bit hesitant to expect positive results, but what we actually found was that within 6-7 months after we put the ore materials in the ground, we actually found appreciable gold above the buried, this is the buried gold ore, and appreciable base metals above the buried VMS ore. And this was in situations where these little plastic trays did not have holes in them. So where we had holes, we had free drainage and nothing happened at the surface. But where we had seasonally perched water, and you could liken this to a water table and a weathering ore body, we actually got that signature at surface. And so, and in the lab work as well, we started looking at, well, what was that material is going to look like and where that gold or that base metals are associated with. And they're basically small particles, ionic, they're charged and they're bound onto the surfaces of clays and iron oxides. And we sort of know that from other work we've done where you look at the surface area of these materials and the absorption capability, and the clays and those sorts of materials have a much greater ability to detect or to concentrate these sorts of signatures. And so we refined the method to basically improve that. How do we optimize our geochemistry? And I go back to and modified some of the slides from Nick Oliver that he presents around pairing the right kind of materials together and partnerships. And I think he uses instrumentation and I can't remember some other methods in his slides. But, you know, I often use this example where pairing, you know, the right particle size fraction and the extraction technique with the right instrumentation will get the best quality geochemistry. So, you know, I think this is, you know, what we've been aiming for, or what Nick would say we're aiming for is George Clooney in his Corvette. We want that better quality geochemistry going forward. However, you know, I would argue that for much of the time, we haven't been focused on that, on refining our techniques. The instrumentation has come along well and the labs do a really good job in that space. But we've probably been operating in this sort of space with George Clooney, but probably not quite as polished as it could be. And likewise, you can really mess it up if you pick the wrong examples all around. So as a test case for that, we've used the Geological Survey of Western Australia's regional soils data and gone back and reprocessed that. And I've presented this before just to sort of highlight how I think typically we've been operating in this zone with our geochemistry for exploration. So here's the original 2000 survey results, and you can see there's one known gold deposit in the area, 4 kilometre space samples here, with some out residual soils and some shallow cover trending into the basin to the north, and almost no gold data in that region, very little picked up. When we improve the method, and this is just looking at separating out those really fine materials and doing the analysis, we improve the results quite dramatically. So, you know, this is, you know, now picking up that interesting gold area. It's picking up some of the mineralization or the greenstone belts extending into cover as well. And, you know, we're getting a bit more information to work with on the exploration front. But I was sort of thinking back onto this, and it was like, okay, well, we're perhaps at the George Clooney point now in the Corvette, but where do we go next? And that's where I think the interpretation and using ML and the next sort of generation of technologies can really assist us in our interpretation. And I wanted to keep the George Clooney motif going. So the obvious one I could come up with in terms of futuristic or improved transport was Batman, George Clooney, and his Batmobile. And so you'll see this pop up throughout the presentation where I'm sort of saying this is where we can go next and then improve our interpretation. And the reason I really want to do that is because of the issues with landscape context. There are a lot of companies that do large grid-based surveys. They aren't often regolith or even geochemistry experts in their companies that can interpret the landscapes very well. So they're just often picking the biggest numbers. Now, in geochemistry context, putting a grid over this will work well. And these are sort of, you know, examples of mineralization. You will see you will detect this deposit. That's the one you're going to find. You might even detect this one with, you know, some shallow laterite sampling or something like that, or soils. However, it's these deposits that are getting overlooked in our exploration through cover. So this is the, you know, your sand plains or alluvial channels and things like that, where the geochemical signature is going to be traditionally much weaker and the landscape is very much different. So it's like, how do we make that interpretation easier to digest? And so what we've done is apply a machine learning landscape process to our geochemistry. And so the workflow is this. Basically, we package up some spatial data sets. In this case, we've used things that we think are very representative of surface landscape type processes. So we use radiometrics, shallow detected uranium, thorium, and potassium data. Sentinel-2, so we use some of the regolith ratios. That there's some published data and reports about, you know, combinations of these from the satellite imagery. There's a range of different options there, but again, using that satellite imagery, direct measurement of the surface in some way. Digital elevation model, really important to understand landscape context. And then we use this product, which is the multi-resolution valley bottom flatness index. It works really well in Western Australia, where we've spent quite a lot of time working on it. It does have some limitations in a couple of other areas, but it is a really nice proxy for depth of cover, and particularly depth of transported cover, where it tends to map paleochannels quite effectively. And we want to break that down because it does really dictate how we can interpret our geochemistry and where we can look for those subtle geochemical signatures. So combining those, we do a bit of a dimensionality reduction and then produce a feature similarity map. So this is that machine learning type aspect going into it. And from that, we then cluster it. This approach does not know that the pixel location. So it doesn't know that the sample next to it is in the same colored landscape or anything like that. So there's no smoothing or anything like that. But you can see in some of the examples you'll see coming up, when it's all placed back into spatial context, it actually does make real landform looking maps. So they do, you know, it gives us confidence in the machine learning approach is pulling out features that make sense. And now I'll show some examples of that. And from there, we can then start to interpret our geochemistry. And this is where putting it into landscape context and a little bit of the output we're doing, which is the sort of analytics package that we're producing as part of our project. That project is just wrapped up now. But you'll start to see more of this, hopefully accessible to industry in the future. So here's an example of some of the regolith maps. So here's those raw data products going in, the digital elevation model, as I mentioned, radiometrics, and the satellite imagery. There's a little bit of machine learning magic in the background, and then these are the sorts of typical outputs you get. So, you know, again, mapping residual materials, usually these dark red and orange colors are the residual settings, and then you can see that transitions off into erosional settings and into depositional planes. And as this gets thicker, trending this direction, the cover is getting thicker, we're separating out those units. On the surface, they actually may not vary much at all. And so we look at that and how they respond compared to traditional regolith maps as well. And so here's one example where we have done that. And you can see a traditional regolith map here with residual in purple, some sand plane and sort of sheet wash mapped. And these are the parameters down below, the four sort of landscape spatial data units that we merge to produce this what we call a proxy landform map here. And so you can see that, you know, some of the patterns hold up, but what we're getting is much more detail in those areas. So it's really important because, you know, often there's limitations on access to sites. People can't map at real detail in some of these remote areas. And so we're getting information producing these maps at about 30 meter pixels, essentially, and they are standing up really well. And here's a Queensland example we did. So we did some work with GSQ in the Jericho area. The area itself was really small, and that's published in a report now, but it's probably not conducive to the approach. But we actually then went and looked at the larger area, and you can see how that maps. So the Jericho area sits just in here somewhere, I think, from memory. But you can see here's the typical surface geology and regolith map. I mean, the regolith map for this area is actually quite detailed. It's not too bad, but there are a lot of other areas where it's not nearly as effective. You can see the spatial data layers that go into it, and then the landscapes that sort of we're producing here. So I'll just show a close-up of that in the next plot, and how that then pulls us into how do we use that to interpret our geochemistry more effectively. So you can see that sort of landform map, and as these are obviously broad alluvial settings, and the cover's getting thicker as you trend down these channels and things like that. And you can see that the landscape map is actually picking that information up quite effectively. And the reason we think that's really important comes back to putting that geochemistry in context, because what most people will tend to do with their, this is nickel in this example, will look at their data set and pick out all the big numbers. That's their anomalous samples. Traditionally in this box and whisker plot here, you can see for the total population, this is your anomalies. And in your residual settings, that's great. You probably find your examples like this, but it's these ones under here that we're missing. So this might be one of those, sand plane sort of settings. And these are the anomalous samples for the sand plane materials, but we're probably not even stopping to go and look at those at all. So what I would think is that these samples here are potentially these samples in this sort of example or block diagram that Charles and Anicia have put together as demonstration for this. So that's the type of samples we're trying to pull out of our geochemistry, because they will be much more dilute signatures in those sort of more active transported cover terrains. And so here's a real example using copper data, where you can see the concentration of the numbers, and the regolith map I don't have, or the landscape map popping up over the top of this, but you can see the triangles in here that match. This isn't the whole survey. Match the anomalies, match the triangles down in this diagram here. So again, these ones are residual settings. They're your standard targets that we will find quite easily with most geochemical methods. However, it's these ones that are up into the transported cover that starts to get really quite thick that we probably overlook completely. These are very low copper concentrations compared to the whole survey. And that's the sort of information that, they may be false positives, but it's information that we don't go back to that we may overlook. So that they might sit, and in this case, they do sit on some really interesting structural trends. And so they're areas that the industry might want to go back and have a closer look at. For the Queensland example, and this is, proof of where certain setting that doesn't work, you can actually see in the landscape we pulled out for Jericho. Again, there's not a lot of landscape variation here, even if we use quite a number of cluster separations. There were no anomalous samples by landscape type. So even though there were some elevated copper results on the whole, there was nothing there. But in this setting, we're at 70 meters of cover, and I don't really expect surface geochemistry to work. So while it would have been nice had it produced something, I think the actual looking through the way the next gen analytics pulls out these features actually says, no, it didn't work, and here's why. But the landscape context has actually proved valuable in possibly not pursuing soil geochemistry in this setting. And so coming back to the GSWA example, though, however, in a regional setting where there is perhaps more interest, you can see here that now not only do we have the standard stuff we did in 2018, with the additional landscape model products, we can now pull out some new targets with some solid background on why they might, one, have been overlooked, but also might be worth further investigation. And that's where we really think we're going with this type of work. And so that is the output that we're generating, but we're also producing things like principal component analysis, a whole lot of exploration indices, regolith ratios, and spectral data analytics are also part of that package. So we'll just show the example web platform viewer we're using at the moment for the companies that we use are using this with us at the moment. We're about to package this up and try and make it more available to the broader industry, and it will look a little different to this. But what it does, it shows your spatial layers, it produces, and you can actually click between a number of your landscape models. And then we've put a couple of other layers in there just for people to look at, you know, gravity, magnetics, and also the comparison to the mapped regolith and surface geology of the area. You can click on any of these buttons on the side, drop down the geochemistry that you want. And here's an example, a big survey. We're looking at zinc. There was only 2 anomalous samples within that whole, you know, 5,000 samples that were done. You know, so not a lot of targets. But when you actually look at those same results with landscape context, all of a sudden there's a whole lot more anomalous samples. And in particular, I'm going to quickly zoom in on this area and just highlight that, you know, that one extreme number, you know, 608 ppm in the soil, is now supported by a number of other smaller values, so lower concentrations, but anomalous samples for that landscape. So this might be areas where there's a bit of cover, or just soils that are suppressed in sort of their geochemistry for, you know, that landscape. And I don't know what the landscapes are for this setting, but it gives you some real confidence to not just be, you know, saying, well, we've got one anomaly, but now you've got a region with a whole series of anomalies in that area. And when you compare it to, this is the mapped regolith geology, you can see the advantage of that machine learning approach to landscape analysis, where you can say, well, regardless if we've never set foot on there, we can produce some sort of landscape map with 30-meter sort of pixel resolution. And then there's a number of other products that we've produced just quickly in the background to give us some other additional properties that we think have value. So these are total organic carbon. This is soil pH. I don't have the scales presented in here or the legends. Soil color, you can get an indication of your soil color. Particle size, textural analysis. So this is sandy loams and silt loams in this setting, or loams in this setting with purple. And some of the spectral mineralogy. So this is kaolinite is pink or well-ordered, and poorly ordered is white, or vice versa. Green is smectite-rich clay. So we're getting information about this material that we can then interpret our geochemistry even better. And I haven't got time or examples to go through that today, but I just wanted to put it out there. But that's where the thinking is going. And this is some other spectral data and principal component analysis. So I hope I've given you a flavour for what we're trying to achieve. It's a big team effort and a big industry supported effort, and that QR code there will link you to our website, where there's a whole lot more information, data, how-to guides, frequently asked questions, and a lot more. Thank you very much for your time.
Wonderful. Thanks very much, Ryan. You are also free of any questions at the moment, so we might just move along to the next talk before anything pops up in there. Hopefully, if anyone's spoke too soon. We do have a moment to answer the question that Mike Whitbread has just kindly put in the Q&A function. He asks, Ryan, which data set drives the clusters the most? DM or the Sentinel?
I can answer that one. Normally I get my hand off to my machine learning guys for these sorts of questions. The MRVBF is what tends to drive the separation of the clusters more than anything. I mean, it is derived off the DM as well. But what we find is when you look at the clustering consistently over a range, and we've done about 50 of these different sites now, generally, the MRVBF, the thickness of cover is the one that really separates out the clusters more so than anything. In some cases, that is also the radiometrics occasionally will play a part, but that's probably the most consistent. And I can see that Mark's asking about the clusters being field checked. We have done field checking studies in some of the cases. It's not for all those cases. So the example I tested, I've never set foot in that area. We do go back to satellite imagery and other data and start trying to zoom in on Google Earth and try and pull out features where we can. But we have done this, we've done a range of other things where we've actually gone to sites, and we've actually mapped a whole lot just in the hills around Perth as test cases to see how the landscape mapping performs. And it's surprisingly, it's not perfect by any means, but it's actually surprisingly good, even when we pick out unusual clusters or a couple of pixels that were like, that's weird that it threw up, some yellow pixels amongst some blue. And then we actually go there and we find a little, a depression within the landscape or something unusual in the vegetation that must be being explained by that. So it's holding up pretty well. And I can
Those
quickly say we are.
Questions are coming in thick and fast. So I might, just in the interest of time, can we either hold these questions until the Q&A after, or you're welcome to type answers if that's all right,
I've
Ryan?
got to jump off before the Q&A, so I'll type some answers in and people can hit me up afterwards for any other questions.
Thank you so much. All right, our next speaker is a PhD candidate from the University of Queensland. His name is Imam Purwadi. I'm sorry if I've mangled that a little bit, but I've done my best. Are you able to share your screen, Imam?
Let me try. Can you see my screen?
Yes, looks good. Thank you.
So, hi everyone. Thank you for coming and thank you for inviting me. And in this session or occasion, I will talk a little bit about my research at SMI. And this part of my PhD defense has been published, and you can see this is linked to my presentations. And my presentation is about a hyperaccumulator. Hyperaccumulator is, a plant that can accumulate or hyperaccumulate some metals. It was a term that referred to Pickering accumulator, a plant that in its latex contains 25% of nickel. And since then, there are around 721 hyperaccumulators have been identified, and most of them is nickel. So there are a lot of reasons why we should find hyperaccumulator. As you can see here, exploration become harder, mining contribute to global warming, and mining endangers some plant species. And by looking for hyperaccumulator, it can lead to mineral deposit. Also, we can do like agro mining with hyperaccumulator, and then we can, make a plan if the plant is in danger. And there are a lot of more than 500 hyperaccumulator is nickel. Then why is that? There's a reason for that. There's an easy tool to find nickel hyperaccumulator. If you see it, there's a magic paper. All we need to do is, to stain it with latex. If the color changes, it's good, which means there's a high nickel on the plants. And if it's not, then there's no nickel or very small. And then there are also a reason why there are a lot of hyperaccumulators have been identified. As you know, there are a lot of outcrop for nickel, and also the price of nickel driving the research on it. But as you know, there's also, the first hyperaccumulator have been identified was rare earth actually, but the price of nickel, rare earth was not that high compared to nickel. But since around 2000, there's rise in rare earth price and demand. So a lot of research on rare earth hyperaccumulator have been performed since then. And around 2019, there's a idea how if we use a portable SF instrument to scan herbarium, because it's quick, and then there are a lot of herbarium specimens. For example, in Queensland herbarium, there are around 5 million, but so far we only able to scan around 20,000. And then how does it work? So basically, the instrument has two main core components. First is the X-ray source. The second is detectors. So the X-ray source will emit some X-ray. Then if the incoming energy collides with the electron inside the atom, if it has enough energy, it will kick the electrons. And then it will leave an empty space here. In this case, the atom becomes unstable. So in order to retain its stability, electron from the outer shell will move to fill the empty space and while emitting some energy. Then the detector will record the emitted energy. And then if you look at the spectrum here, you can see it. And if you look at here, the blue one is the spectrum. And then each peak represent elements is unique. And you can see here if you want to see what this peak belong to. So cobalt. Yeah. And then there's a caveat in the portable SF instrument because it's not perfect and also it's not designed for leaf. For example, here this is a case where I often see the gray one here is the spectrum of the sample. As you can see, there's like a nice peak here. It's belong to Ethereum, but the instrument failed to report this. And then even like this one, it has cerium. It's nice peak, we don't see noise, it's clear, but the instrument failed to report this. So we missed some informations. Also, the problem with herbarium, we cannot destroy them. So we measure as is. And for example, in this green one, is represent the thickness of the herbarium, 250 microns. So imagine the portable abstract instrument assume that you prepare the sample and to meet the sample with the thickness requirement. The thing is that the thickness requirement for each element differ. For example, here, for this element, it meet with the thickness requirement, but for element above this one, starting from argon, potassium, calcium, it doesn't meet with the requirement. So what will happen is that something like this. This red dot is actually the concentration reported by the instrument. It's based on the sample with the same concentration, but varying in thickness. So for potassium, it has, because if you refer back to this image, potassium here is close to meet with the thickness requirement, with the thickness 0.1, still okay. But for zinc, because it doesn't meet the thickness requirement, and if we don't correct it, then even though like the concentration should be around 1,400, there will be like reduction in half. So this white one is like theoretical concentration if you don't correct it. And then next is how to deal with this. So we need to think about the thickness, and then we incorporate the thickness into the calibration. So in herbariums measurement, we usually put a titanium plate or pure plate underneath the specimen, and then we, based on this, we know that based on this the titanium signal can travel in the herbarium matrix around 2 millimeters. So it's enough to pass through the herbarium, and then the detector will record it. And then if we see this, this is an illustration that we hypothesize if there's nothing on top of it, the concentration will be high. And then as we put something on titanium plate, the concentration will be reduced because it's absorbed by the sample matrix, and there also enhancement and absorptions. Then this is the calibration line for to get the thickness or RR density from the titanium plate. So we fix that, we correct them, and we get the correct concentrations. Next, after we correct them, the next step is to to see how good is the method. And then as a background, hyperaccumulator in Australia only around 10 species. And then as we know that Australia has a lot of metal-rich deposit. Even the soil has high amount of metals. And we also have around 2,000 herbarium specimen measurements. So we try to reprocess the data, and then this is the result. So this is the species that was not reported before by the previous study, but with the developed method, we can see that there are a lot of new hyperaccumulator. We missed this information, and even these two species, they have been confirmed by taking this new sample from the field, measure them in the lab with ICP. So they are real. It's not false positive. And then by measuring herbarium specimen, usually on the herbarium specimen, you can get the location where they were collected, and then we can plot it where they are. So this is manganese, this is cobalt hyperaccumulator. Basically, the herbarium has more than 300. Nickel, it has more than 1,000. Zinc, it has more than 3,000. So this is the two new rare earth hyperaccumulator. This is Heresia. It is species we took from Eagle National Park from Queensland. And if you compare the, can you see? Yeah. If you compare the concentration of rare earth compared to rare earth in other rare earth hyperaccumulator, it can be seen that it has enrichment in EVRAE. And then we plot the location where they were collected, and then interestingly, they are coincide with granitoid rocks formations. So it can be used as an indication for explorations. Next is about when we measure for hyperaccumulator leaf or herbarium specimen, we want to know whether the concentration is okay or above abnormal. So this number is the threshold to indicate whether the plant is hyperaccumulated or not. But we want to check if this number is correct or not. To do that, I collect around 27,000 herbarium SRF data from 4 different countries. We process them and to check that number. And also we have ICP data for leaf from Malaysia. The first thing that I did was to clear the data because, as you know, XRF has high detection limit. There are a lot of below detection limit, so we need to deal with this number. So to do that, we use regression on order statistic. Basically, this is the concentration, this is the quantiles, and we try to extrapolate the value and to make estimate the value around here. And if there are a lot of method how to deal with non-detected value. You can use a constant value, but if you use a constant value, this will be like a 1 bar very high here. And if you do like a statistical analysis, it will throw some errors because, for example, if we fit 2 models, one for hyperaccumulator, one for a normal hyperaccumulators, for this model it has a standard deviation of 0, which doesn't make sense. So if we use regression on order, we see here it preserve the original data and then fill the data here nicely, and then we can do some mixture model analysis. And this is for ICP data for nickel concentration, just like the model pattern clearly indicate this belong to high concentration, this low. So that's how we fill non-detected value, and then after that we fit to model. The green one represent normal plants, the red one represent high accumulator, and this vertical black one indicate historical value. For example, here we saw that for nickel we get 1000 value, but based on this analysis we think that 280 is already high enough. So this is similar with ICP data. This is based on SRF and ICP data. This table summarizes our result. So if you go to the field and measure it with ICP or SRF, we can see that if the concentration, for example, for cobalt is more than 32, there's anomaly here, and then maybe you can do some further investigation on that. So we realized that there are a lot of manufacture of the instrument. So we think that we want to know how good is the developed method. For example, here we have 3 different instruments. Can we make the result from the 3 instruments comparable? And then if not, if we don't make them comparable, then we combine them together, there's like, for example, this tool on the left might underestimate the concentration, the middle will be about right, but on the right, maybe they will like overestimate the concentration. So based on the default method, we try to see if the default method can make the result comparable. So in this case, we use 3 different instruments. We use around 100 leaves and 3 different algorithm manufacture, which is in-built algorithm. The second is empirical calibration, and the last one is independent pipeline we developed. So if you can see here, I will show this. If you can see here, this is represent the spectrum from the same sample, but from the 3 different instruments. They have different anode or source. Here they have molybdenum. Here in the middle they have rhodium, and this one they have silver. From this one we can see they are unique. They have different anode, and from lower energy we see that this part they didn't detect calcium, sulfur, which means that the detector maybe not better than the 2 instruments. So we apply the algorithm and compare the instrument and algorithm, and we see that for the independent pipeline which we developed, it has a better accuracy, and it's indicated by this green line. This is. So we expect that in the future, if we use different instrument and we apply the same pipeline, we expect the result will be comparable. Next is about proof of concept. So basically, my background is remote sensing, and then I want to try if we can sense metal in hyperaccumulator plants, because hyperaccumulator contain very high amount of metal. Whether they can, make the spectral reflectance difference from normal plants. So there are also a reason why we use this approach, because for example, to operate a portable XRF instrument, you need a license in Queensland. Also, it can be used to reach a remote area, and then it can be scalable. It's not only from one pass, but with the hyperspectral satellite images that are there, we hope that we can use that to find hyperaccumulators. So if you're not familiar with remote sensing, this is how it works. So basically the sun will emit some light, and then it will touch the leaf, and then there's a possibility that the light will be reflected, absorbed, or transmitted. And then the reflected light will be recorded by a sensor, and then this is absorption due to chlorophyll. And if you see this mostly done by absorbed by water molecule. So the next step is to do some literature review. So here we have a normal reflectance of plants. And then, for example, when we do some manganese, we have a lot of manganese hyperaccumulators, but the band absorption of manganese around here, which means that we cannot see it. The light around here will be absorbed by chlorophyll. There is nothing left to be bounce back or reflect back. And then we have also manganese here, the same, but cobalt, iron. Yes, there may be, if the plants have a lot of iron, there may be absorption around here. And then if it's neodymium, we expect to see 3 absorption band around here. And then if it's nickel, it's around here. Then based on this information, after a literature review, we see that our focus should be spent on iron and neodymium and nickel, but because we only have a nickel hyperaccumulator on our lab, so we focus on nickel. So in that case, we managed to collect 8 species of nickel hyperaccumulator, and then we do some measurements. Here, the nickel concentration of each species, as you can see here, this is the threshold for hyperaccumulator is more than 1000, and there's no sample which has concentration below 1000. Yes, because they are hyperaccumulator. And on the right panel, as you can see here, this is only as an illustration. There's a decrease in reflectance as the nickel concentration increase. And then here is the mean spectra of each species. As you can see, the white one here is the normal leaf. Usually in this region, there's a peak, whether it's in a fresh or dry leaf. But here we can see that there's an absorption here. There's like a little valley here, which means that there's something that absorbs the light around here. So after that, we got the reflectance, we get concentration. The next step is to build like a 3D cube model, reflectance in X and Y, and concentration in Z. And then we build a correlation map. And as you can see here, it's quite complex a lot. But if you focus on this around 1150, there's like a axis here, and around here we can see that here. This means that there's the difference in reflectance of absorbance related to 1150. There's something that absorbs it, and then we hypothesize that this nickel, and based on this sample, it could be nickel. So next, this is extra. We also do some sample collection on the rock that we collected. So this is a hyperspectral. So we take a picture of the rock using hyperspectral camera, and then we sample one of these pixels, and then this is the spectrum, and these 3 absorption is due to neodymium absorption. And then we combine them. For example, here is the RGB image of the rock containing red earth, and this white here is, we do some processing and highlight where the neodymium is white, and this red is this is a elemental concentration map using micro XRF image, and then the red one is area with high concentration of lanthanum. So there's like corresponding area indicated by both image. So if we use hyperspectral images, we should target for neodymium, and then if we use micro XRF image, is dependent on the energy. For example, for CMM, we use lanthanum. So if you are interested in remote sensing for Red Earth, I've presented here, as you can see. And then if you think that you missed something or your data, feel free to contact me, then I can help you to process the data. And thank you. And this presentation is here for the full session. And yep, that's all from me.
Wonderful. Thank you so much, Imam. We don't have any questions for you at the moment, and we are running right on time, so we might move on to the next presentation, but people will have an opportunity to ask questions in the Q&A in about 25 minutes. So thank you very much. Our final presentation for today is an industry point of view. So we've got Luke Pickering from South 32 joining us. And I can see those slides, but I cannot hear you yet, Luke.
Oh, thanks, Janelle. Yeah, just getting my computer set up. I'm just at the Greenvale Roadhouse. So sorry if a truck drives through and makes loud noise.
Wonderful, thank you. Take it away.
Okay, let me just... Okay, so yeah, for those that don't know me, my name's Luke Pickering. I'm with the South 32 exploration team. A couple of weeks ago, Evan reached out to us and asked would we be interested in presenting today, and we sort of felt like we had to, because a lot of our projects are sort of exploring undercover. So yeah, we sort of felt committed to do this one. So I put something together, and I hope you enjoy it. I guess a bit of a rundown just on some of the projects we're looking at. One of our projects will be Ifley, just north of Julia Creek, BHT prospect. Have a quick look at some of the Jessica and Carrara joint venture that's going on now. Some of our tools, you know, a tool we're looking at to deploy in conductive terrains to target basement conductors. And then, you know, Joe and has already spoke a bit about Tulivuk, but that's one of our projects that we've applied for last year. And I won't probably spend too much time on that one because Joe's done a lot of the talking for me, but so thanks, Joe. So this is Ifley. You know, it's probably an interpreted basin of siliciclastics and volcanics. When we applied for it, you know, the interpretation was potential for Soldier's Cap group and BHT style mineralization. Very limited drilling in the area. You can see evidence for ductile folding of the magnetic stratigraphy and fold closures. So we thought, oh, it could be stratigraphic thickening in these regions and possibly mineralized horizons. So we wanted a better handle on constraining the depth of the basement in this area. So we deployed passive seismic to help try and constrain that. So passive seismic is sort of a quick and easy tool to sort of measure the depths of bedrock, you know, below poorly consolidated cover. So you can see on some of these pseudo sections. One of the benefits is that you're also able to interpret paleo highs in the basement, just subtle ones. The resolution's probably as good as what you see there, but still you can interpret those basement paleo highs, which sometimes will line up with some of your interpreted structures. So seeing that gave us confidence in our interpretation and sort of gave us a depth to aim at. So we planned a few drill holes into some of those key structural positions and that. Initial results, visually, in our first hole, we got into some BIFs and some molted quartzites. So we thought, oh, this could be equivalent to Mount Norna that we see around Cannington. And, you know, some of the sediments look like Soldier's Cap group, but, you know, some of the preliminary dates you can see there, we got Egri to do a couple of dates for us, and probably put a lot of that in the Wonga, sort of Wonga aged equivalent. So probably a bit older than what we were thinking. Maybe that first hole where you can see the quartzite there, maybe we're just on the fringe of some of that Soldiers Cap group stratigraphy, but basically a lot of it was a lot older. Some of the mineralization you can see there, these pyroxene, pyrrhotite, pyrite sort of overprints that you see a lot in the Eastern Succession. But unexpectedly, we also got some molybdenite chrysotile zones in that second hole. They were pretty deep, so we didn't really want to follow those up at those sort of depths. So based on those age constraints, we were likely a little bit too deep in the stratigraphy for Soldiers Cap group, but we're thinking it probably, if it exists, it's probably further to the east. I guess the takeaway is passive seismic was a relatively quick and easy way to estimate our basement, plan our drilling, you know, in this sort of covered terrains. You probably won't get the resolution of a seismic reflection survey, which if you want to interpret basin architecture and structure, that's what you want. But if you just want a rough and ready depth of basement, passive seismic's a pretty good technique. Next, we'll sort of look at some of the interpretations from seismic. So this is our GSQ and Carrara project. It's a joint venture with Encounter Resources. I think it's probably fair to say this is one of the most enterprising greenfield plays for sediment-hosted base metals undercover at the time. At the present time, that's not being arrogant. I think that's just because the amount of interest and on the back of all the pre-competitive data that's been generated and made available. You know, so you know, that's from the initial seismic work from the GA through the NTGS with their gravity, and then you know, right through the NDI Carrara drilling and all the CSIRO and results that come out of that. So I think it's a good one to bring up in this forum. Here we have GA's sort of two-way interpretation of the Carrara subbasin there to the east. You know, they're interpreted faults and metal-stratigraphic horizons. The section suggests, and I think everyone sort of agrees, that the Carrara subbasin is just an extension of the Lawn Hill platform to the east, which hosts the Century deposit. And I guess that NDI drilling in 2020 was really the icing on the cake for the Carrara interpretation. You know, so it's fantastic. It's a fantastic foothold to have, you know, when you're exploring in these sort of terrains. Extending that Lawn Hill platform interpretation further west and identifying, you know, time equivalent packages. That's one of the aims of our initial drill program, which is it's not easy when you have basins on other basins. So it's quite a complex area, but we've got a real good head start on all the work that's been done. You might have seen that drilling started in July. So if you want a bit more information on what's been going on there, I think Encounter made a release a couple of weeks ago on some of the initial results from the Zeta target in the northwest there. So if you wanted a bit of an update, I'd check out their announcement. One of the tools we're looking to you know, roll out in some areas is a low frequency airborne AEM survey. So I guess it will help. The plan is, the geophysicists tell us that it'll help differentiate between conductive overburden and potential basement conductors, which may represent target horizons at depth. So whether it works or not, don't know. We haven't tried it yet, but this is one of the tools we're looking to deploy. So I like it because I guess it shows the progression of our methods in the industry. It's a traditional exploration method, but now it's been refined and being applied to previous terrains that we probably wouldn't get many results. So the geophysicists also tell us that we'll probably still get graphitic false positives, so we might have to filter anything out with some secondary techniques. This is our Tulibuck project. We've heard a lot about it already today, thanks to Joe and a lot of the work that GSQ and CSIRO did in their sampling from a couple of years ago. So yeah, real feather in your cap, Joe and all the team. It's one of the main reasons why we sort of looked at this area. So as you, I guess, when you boil it down, the garden bore, which you can see there on the map, it's got a very comparable isotopic signature to Kennington, and it sits on the isotope growth curve. So just having that extra piece of information, and then you add in a bit of interpreted geology, it can really enhance the prospectivity of some of these historic magnetic and density anomalies that are in the area. So just having that extra bit of information, it really changes the way you can look at an area. Just takes that one sample. So this is I think a real excellent example of industry sort of taking up some of these initiatives and getting on and taking ground on the back of some of those. Just some of the next steps in our projects. IFLI's been relinquished. Like I said, we're more targeting Soldiers Cap Group stratigraphy for BHT style mineralization. So we still think it's prospective, but probably further to the east. So we just got to try and identify areas where it's shallow enough, to warrant us going in, and where the potential for the Soldiers Cap Group still's high. Jessica Carrara, as I said, drilling's underway. So probably finish that hopefully soon. Some of the petrology and the age dating, I think, is really gonna bolster or change the way we sort of think about some of these interpreted basins west of Carrara, where we don't have as much drilling to constrain it. And like I said, Tulibuck, look at some of the historical surveys, maybe fly one of our own. It's still in application phase at the moment, so as soon as that gets granted, we'll be looking to hit the ground on those. When I got the presentation schedule, I noticed that I was in the go home slot, so I thought it was my responsibility to sort of provide a bit of closure for the session. And I think it's important to remember that what we're doing when we're exploring undercover, it's not easy. There's no silver bullet, but we have made some great steps, and there's a lot to look forward to. Some of our best discoveries were undercover. I think anything one of these today would just totally reinvigorate the resources, or especially exploration. It just totally changed the way everyone sort of feels. Our knowledge of these systems has never been better. Whether it's access to the data, to high quality data, consultants, understanding increases every day. Every conference that you go to, there's something new that we can apply. And that it just adds to our ability to predict when and where large deposits might have formed undercover. And finally, there's never really been a better time to be in exploration, I think. Anyway, this is my views. We're increasing demand for traditional new commodities. It's like we're looking for the whole periodic table at the moment. Everything's on the table. I think we can operate in any environment. I think, especially in Australia, barring the northern wet season, we could really plan a drill program and execute it to a budget. I think in anywhere in the continent today. Like I said, with methods and techniques, is this getting better, as we see with the low frequency EM? Applying that to previously terrains where it would be ineffective. And I think, and finally, our attitude to exploring has changed. At least in my time in the industry, I've seen it change a lot. What sort of seemed ambitious when I first started is just pretty vanilla now. So I'm really excited for what the future holds, especially with our projects, but also just in general, especially with some of the talks that was heard today. You might have seen at the start of the slide, I had an image of myself divining. 100 years ago, that was probably the pinnacle of undercover exploration. You send a guy out with a divining rod or a stick, but look at us now. So it's a really exciting time, and thanks Janelle and the GSQ for organising this, and thanks to all the presenters.
Thanks very much, Luke. You've done my job for me. You've wrapped it all up beautifully. I don't think we've got any questions for you at the moment, but we do have our Q&A session coming up in just a moment. I'm going to sneak in just before we go to our Q&A session with a very cheeky plug. We have our Digging Deeper event coming up. This is the Geological Survey of Queensland's annual showcase. It's on the 23rd of November, and we already have over 200 registrations for this event, so you better get in quick if you want to come along. There's a focus on in-person attendance. We will be recording all of our talks, but we're not going to be streaming them live. So if you want to get all of the knowledge as soon as it's presented, it would be great to have you in the room. We're at the Convention Centre on South Bank. So I will stop the shameless self-promotion, and I can see Rick has his hand up. Did you have a question, Rick?
Yeah, I had a question for Luke. Great talk. Really enjoyed it. And I took your advice, and I've been going away and looking at the Encounter website and the announcement about the Carrara drilling. It's great to see, the commitment to do sort of greenfield drilling like that. And given that the target that you're after has had quite a lot of study in terms of what the halo might look like. And obviously there's quite a bit of variation from example to example. But my question is, have you got kind of a framework in your mind of, I mean, it'd be great to hit the ore body in the first 3,000 meters of drilling, but there is a reasonable chance that you may, just wing the ore body or get some results that need to be interpreted in terms of the zoning and to make a judgment as to whether you're in the right environment, that there's an ore body there somewhere, even if you haven't hit it in that first 3,000 meters. My question is, how detailed a sort of set of criteria for distinguishing between encouragement, discouragement, success/failure have you got in your mind?
Yeah, thanks, Rick. Yeah, good question. I guess with that initial results that Encounters put out, that was I think it was an IOCG target, and I don't think what they've put out has downgraded that area. Just from the limited drilling that we've had. So yeah, quite optimistic. You know, that's just the initial core that they sort of got out. So they still have the geochemistry to get back whenever they get that in, you know, and then petrology work, and then all the other you know, near miss and indexes that we can apply to it. So yeah, my response would be I don't think it's downgraded it. I think it's supported that sort of concept. So looking forward to when they get those results in.
Yeah, but they drilled on another tenement. They drilled on Jessica, didn't they? And you're drilling on Carrara, is that right?
They're drilling on both.
Oh, okay.
So it's sort of, they're two separate projects, but they're I guess the Jessica one is the western basins.
Yeah.
The western basins of Carrara. So they're slowly got other holes planned for that area.
No, so I wasn't passing judgment on the, you know, whatever the results were from that first drilling. It was more whether and you know, anything you could share about what actual criteria you were using in terms of you know, what you might look for in terms of, you know, mineralogy or geochemical results. Or I know it's probably a question that's difficult to answer and very dependent, but there's you know, given that there's been quite a lot of study of the sort of halos around this style of deposit, I was just interested to know whether you were using some of that information in more detail, or whether you were just going to see what was there and then use that information afterwards, type of thing.
Yeah, no, I think we'll try and get the plan would be to try and get as much information out of those drill holes as we can. You know, it's pretty deep drilling, or not deep, but you know, it covers about 400 meters of Georgina Basin. So it's easier to do as much work as we can, similar to the Carrara drilling. You know, they got a lot of information out of that stratigraphic hole. So we probably want to squeeze similar amount of information, albeit it's probably a different exploration target, that side. But yeah, we'll be looking to definitely get more out of that. That's for sure, Rick.
Thanks.
Thank you. I believe we've already started the process of promoting people to panelists so that we can all join in the Q&A. So does anyone have any burning questions for any of the presenters that didn't get a chance to ask them previously? You're welcome to just unmute yourself and ask a question. See, Tom Evans has his hand up.
Unmute myself as well. I got a question for Brandon. It's about the isotope compositions of the copper reservoirs that are being sourced there. Has there been much work done on characterizing what these copper isotopes look like? I know Jan's done a bit of work on that and published recently on it, but I'm wondering, with these deposits, if there's much variation in what the composition of the sulfides that are weathering into the water table is, and whether it's different to, say, the composition that you might get from copper that's weathering out of big basaltic areas as well, like what the composition of the ECVs or the Tall Creek volcanics is, and you know, whether you could distinguish basalt copper versus sulfide copper or deposit of copper.
Yeah, that's an excellent question, Tom. So there has been some sort of collated information, I believe, in the GSQ report that Ryan had led. There is a couple of violin plots in there that basically looked at, you know, what the general sulfide compositions were relative to the expected and or hypothetical groundwater isotope compositions would be. So you have a look there, and there are some papers out there that have sort of looked at the sulfides relative to hosts. I'm happy, like offline, I can try to bring a couple of those together and send to you. In terms of trying to pick apart a weathering signature in the water from the basalt, from like basalt or whatever the case may be, versus the sulfide minerals, I don't think there's been a whole lot there, but I think part of that too is the fact that the copper concentrations just by nature in the sulfides relative to the host rock is going to be so much higher that it would be, you wouldn't necessarily pick apart the inputs from them, because you would also need to do the mass balance consideration of how much could be coming out, given like, you know, an actual mass or volume of host rock or sulfide that has been weathered, if that makes sense. So yeah, I don't think there's been too much there. I do think it's a really great question and something that we can and should be looking at, but there definitely has been some of that basically collation of information about the sulfides, especially, and their hosts, and then somewhat separately the sulfides in the groundwater.
Thanks. I'll hit you up offline and have some references for that.
Yeah, sounds good.
That,
I've got another.
I was going to say, do you want to ask your question, Rick?
Yeah. I've got a question for Joe. And this is I might have asked you this question before, but because it's sort of, I can't get it out of my mind, but I haven't done anything about it yet. I'm still really intrigued by the high rare earth results from the Cape York region, and I know that I've heard the argument that it's related to weathering or something, and I remember all the arguments about why the Tick Hill gold anomaly was spurious as well. So I don't necessarily think we should explain anomalies away before fully investigating them. But one question I wanted to ask was, the interesting thing to me, you know, speaking as a complete non-geochemical expert, is that, you know, when you get a copper anomaly, you usually say to yourself, well, that's a copper anomaly, and I bet the minerals associated with that copper anomaly have got a lot of copper in them. But if you get a rare earth anomaly, then some of the minerals could be bastnasite or something like that you could actually produce rare earths from, and some of the other ones might be trace rare earth silicates of various different types, or something in between, that would be where you could get a strong rare earth anomaly that meant nothing. And one thing I thought would be a really good idea would be to take the geochem, you know, because I think we've got coarse rejects from a lot of those samples, and actually do do some sort of characterization on them to say, to take the top, you know, the drainage basins for which we have rare earth anomalies, and say, okay, well, this drainage basin is associated with rare earth mineralogy that we could actually produce if we found a deposit, and this anomalous drainage basin is associated with rare earth minerals which we have no, you know, if we found the concentration of rare earth minerals, we could never make a deposit out of them. Do you think is there some reason why that isn't a good idea? I've been completely ineffective in convincing anyone that it's an idea. I mean, it seems like one that's worth pursuing to me, but I'd be really keen to hear your thoughts on it.
Yeah, GSQ has engaged Awesome, Brett Dark, to look into this rare earth anomaly. This is as part of this IPI, industrial priority project. And the conclusion is that a lot of these rare earths are shaded, from the Cretaceous Rolling Stone unit as, heavy mineral sands within the unit itself. The big question is that where does this come from? Looking at the composition of those sandstone, it has to come from some granites, and we haven't actually located the primary source, but we knew that it's really high within the Rolling Stone, the Cretaceous sandstone itself. So the big challenge now is to find out which granitic unit is the source of that rare earth, and it's mostly in monazite, in one of those heavy mineral sands. So no, it's an area that we need to look at, for the primary source, but we know where the secondary source comes from, mainly as detrital, sort of heavy mineral sands.
And but the so okay, well that's good to know for York, but there's lots of other areas of rare earth anomalism in the state-based, well, it's in the national database, and so I guess the original question about whether it's worthwhile to actually look at the mineralogy of those samples might still apply, but anyway, that's good.
I think that's where this project, that GA is doing with Curtin Uni to look at this, the heavy mineral concentrate from this catchment, samples. And that's one of the proposals that I like to put up, for the next round of funding, to just look at, the actual mineral composition of those heavy mineral sands or mineral concentrates to see exactly where this, what sort of mineral and possibly what could host the rare earth itself.
Good, thanks.
Yeah.
All right, we don't have any more questions in the Q&A that haven't been answered. Do we have any more from the floor?
I've always got questions. You just need to tell me when to shut up. That's the key. But yeah, I've got one for you, Luke. That was fascinating talk, and such an interesting, diverse group of prospects you get to work on. That's very cool what South 32 is doing. I was wondering that the Ifley prospect you're working on. I know you've dropped the ground now, but one of the slides you showed, one of the pictures you showed from there could have been from one of the copper prospects, Scarny sort of things near Mary Kathleen. It looks, identical to what we get around Coppany or Elaine Dorothy in that kind of area. And you said it was Wonga aged as well. I was wondering if you sort of this might be a really interesting geological story there, because it's a fair way from Mary Kathleen, that ground, isn't it? I didn't quite see where it was on the map, but if there's something going on related to what was happening around in the Mary Kathleen belt versus what's happening down at Ifley.
Yeah, thanks, Tom. Yeah, but like I said in the talk, it sort of reminded me of stuff you sort of see in that sort of Eastern Succession or the Mary Kay belt, that pyroxene, sulfide assemblage overprinting. So I guess in terms of thinking of it in terms of the bigger stratigraphic picture, it's probably a bit more that area is all undercover, right? It's a lot more complex than what we sort of think at the moment, and I don't know if you always want to look for Mary Kay sort of style mineralization as well, but I guess we sort of hit a wall with, we come in there with the BHT sort of concept. We couldn't really progress that very far. So do we want to start all over again? And if so, how would we do it? So that was, I guess, the rationale for, terminating that project. And we got other stuff as well, but that was, those age dates, there are, Yuan and Egru sort of did a bit of work for us. They're just a couple of samples. So he said sort of take them with a grain of salt, but but I sort of tend to believe them, and those intrusives are all pretty foliated, and it makes sense if they were sort of a Wonga age as well, So, but just a little glimpse into the underlying stratigraphy in that part of the world.
Yeah, cool. It's a fascinating story there, and I hope, it's more of an academic sort of picture now. I hope someone picks it up and has a closer look at it from an academic perspective.
All right, I'm going to leave the floor open. We've got only a few minutes left in our allocated time. So any last minute burning questions? Yep.
Super quick question to Luke. Thanks a lot for, I really like the industry perspective there, and giving props to the pre-competitive data that you know, people like myself and GA and GSQ we work on and deliver. I'm just wondering what type of pre-competitive data really, you know, like works best for you? Do you like I guess say just geophysical data sets that are released on their own, or the interpretive product on top of that? You know, reports about that. Like what level of I guess use do you find out of those different data sets?
You're muted, Luke.
Thanks, Rick. Yeah, thanks, Seb. Like I was saying, whenever some new initiative or new technique sort of gets emailed to you, and that, like, the first thing I think of is, does this apply to my projects? And if not, could I apply this to maybe some vacant ground and build up a project? So I guess in terms of what we're looking for, like personally, I don't know, like, because there's no right answer, right? Like, there's so many different things. What works in a certain area, say like the hydrogeochemistry down in Tulibuck, it might not work in another area. So I guess it's really just sitting back, waiting for these results from these initiatives, from this research that, like, you're doing, and GA and CSIRO, waiting for the results, and then giving it an industry application. And that's where I see the benefit is. And you know, additionally, some of the stuff that might get released might not be applicable right now, but in the future, definitely, you know, like, you know, we've looked at, you know, historic sort of stream sediment sampling up in Cape York that the GSQ sort of looked at. I think we presented some stuff last year. Cruikshank sort of did some stuff, I think, in the early 90s we looked at. You know, so at the time, probably wasn't applicable, but coming back and having a second look, it sort of made a bit of sense, you know. So sorry I couldn't give a better answer than that, mate.
No, that's all good. Thanks. That's all good. Makes a lot of sense, you know.
Yeah, but yeah, just rest assured that anything that you might be researching, you know, this goes for anyone listening. You know, people are looking at it and thinking of how to apply that to their projects.
Cool.
Even though it might not seem like that sometimes.
Thanks, Luke.
I think that's a wonderful note to end the webinar on, making sure that we all feel valued in the work that we're doing, even though sometimes it can be very, very frustrating producing these data sets on our side. So I just wanted to thank all the presenters and all the people at UQ who have helped put this together. And Evan Marshall, big shout out to you, who works tirelessly behind the scenes to put these webinars together as well. I might draw this one to a close there. Thank you all for being a part of this one.